Rolling bearings are a classic example of condition monitoring based on structure-borne sound. With increasing wear of the bearings, the acoustic fingerprint also changes. At the latest, towards the end of the bearing's life, it becomes noticeable due to a high noise level. In the simplest case, the RMS value can therefore be used as a damage indicator. However, damage becomes noticeable earlier. The first defects appear, grow, and can lead, for example, to small material fractures, so-called pittings. When rolling over such defects, subtle structure-borne acoustic pulses are generated, which propagate as a shock wave via the rolling bearing and can be detected and analyzed with acoustic emission measuring systems. The setup shown here consists of two bearings that are powered separately. The rotational speed can be adjusted via a potentiometer. A VS150M sensor is mounted between the bearings on the mounting plate. The sensor signals are acquired by the condition wave, a two-channel acoustic emission device, pre-processed and transmitted to the PC via the network. The left bearing is undamaged, the right bearing is severely damaged. The differences between the bearings can be clearly identified in the spectrogram, both acoustically and visually. The impulses that lead to a harsh noise impression have a broadband effect and clearly stand out in the frequency range from the operating noise of an undamaged bearing. Based on the differences in the frequency range, a model can be trained to distinguish between the intact and defective bearing. For this purpose, training data of approximately 2 minutes is recorded from each bearing. Since a defective bearing can already be detected via the sound level, the rotational speeds of both bearings are adjusted to such an extent that a separation of the bearing conditions is only possible via the spectral properties. The training data are stored in two different measurement datasets, OK and not OK. The classification model is trained with visual class. For this purpose, a new project is created, and the various measurement datasets of the classes OK and not OK are specified as training data. Spectral characteristics or features are now extracted from this data. At this point, only a rough outline of the workflow is presented. Each feature on its own still shows a strong overlap of the classes OK, not OK. However, a higher selectivity can be achieved through a systematic combination and transformation of features. The next step is the feature selection. At this stage, the features are evaluated and selected according to their separability. The top 50 features are selected as a first attempt. The final step is the actual training of the model based on the extracted and selected features. The classification accuracy with previously unseen test data lies at 95.8%. As anticipated, the classes, here green OK and red not OK, can be easily separated due to the selected and transformed features. With the help of an automatic parameter search, the settings of the feature extraction as well as the selection can be optimized. Here, you can see how the number of features is automatically optimized. The aim is to maximize classification accuracy in the test data and avoid overfitting the model. After optimization, a classification accuracy of 96.9% is achieved on the test data. The model can then be exported with the optimized parameters. With the exported model, new unknown data from rolling bearing measurements can be classified offline as well as in real time. To do this, we start a new measurement. For the current acquisition, the feature extractor is also started, which receives a link to the current measurement file as well as to the exported model. As soon as a new dataset is recorded, the features for it are extracted, selected, transformed, and the classification result calculated. The measurement data is visualized with Visual AE. To display the classification results, we create a new diagram and select the result from the feature extractor as the data source. Despite the standstill of the bearings, class 1 is displayed as OK. Why is that? We have created a classification model that can only distinguish between two states, OK and not OK. The stationary state is unknown. Even if the state is far from the known states, the classifier must decide on a class. A possible solution is to train the stationary bearings as another class, hence the noise of the measurement chain and possible ambient noise. However, since the state differs so much from the operational bearings, a simple RMS threshold, for example, may be sufficient. For this purpose, we implement a short upstream logic that classifies all datasets with RMS values smaller than 20 microvolts as standstill or class 0. For larger RMS values, the result is given by the classifier. Now, the stationary state is correctly displayed as class 0.